Welcome to this video lecture on optical and microwave engineering. Today we are going to discuss about microwave semiconductor devices. So what are microwave semiconductor devices? So these devices are particularly used in high frequency, so which are includes microwave diodes, pin diodes, varactor diodes, impact, rapid, gun diode, etc. So these are the diodes used for oscillation or amplification purpose at high frequencies, and also it is used as mixers, modulators, so like this. So at microwave frequencies, conventional components like transistors, diodes does not function because of the significant inductance value and internal capacitance values and high transit time. So because some specific microwave semiconductor devices developed for high frequency application are used for high frequency amplification or oscillators. So for example, now we are going to discuss Gunn diodes. So Gunn diode is a microwave oscillator. So they generate microwave signals between 1 GHz up to around 100 GHz. So these devices are also known as transferred electron devices because they use the principle known as transferred electrons. Here the only electrons are used. So it is referred as a diode, but it does not possess a PN junction. Normally in the PN junction diode we have P-type semiconductor and N-type semiconductor, so there is a PN junction in between. But in the Gunn diodes there is no PN junction, so it is named after the discoverer J.B. Gunn. So it is normally used for generating the RF signals, and also it can be used as an amplifier. So it is known as the transferred electron devices. It is constructed from N-type semiconductor. So materials used is the gallium arsenide material or indium phosphide, which are direct bandgap materials. So it has a N-type bar with N plus contact. So only N-type semiconductor is used. So here we can see the construction. So there is an N plus contacts, and in between active layer is N-type semiconductor. So this device exhibits a negative resistance characteristics at a particular voltage. So it is used for generating the radio waves. So here we can see the characteristics of Gunn diode. It is the voltage controlled negative resistance. So here the graph shows the voltage current VI characteristics of a Gunn diode. So when a threshold voltage is reached, the current becomes decreasing. So we can see a graph. Initially the current is increasing when we are giving a voltage, but after a point, first peak point, there is a decrease in the current. So it is the transferred electron effect present in the Gunn diodes, and it is known as the negative resistance region. So here the device exhibits the negative resistance on its VI curve. So the reason is here we can considering the energy band structure where valence band and conduction band is present. So in the gallium arsenide materials there is a lower valley and upper valley present in the conduction band. So when we are giving a voltage at a particular threshold voltage, as the electric field increases, the electron drift velocity in gallium arsenide reaches the peak value and then it decreases. So the energy of the electron increases, and then the electron can be scattered into upper valley. So it means the mass of the electron is high in the upper valley, so that the mobility decreases as well as conductivity also decreases, so that the current decreases, as we have seen in the previous graph. So this is the reason we are getting a negative resistance graph. So this effect is known as the Gunn effect. So here the inventor Gunn discovered a random noise like oscillations when biasing the N-type gallium arsenide sample above a certain threshold value. He also found that the resistance of the samples dropped at even higher biasing condition, indicating the negative differential resistance. So here we can see the oscillations are produced after a threshold voltage. So here the sustained oscillations can be obtained using the Gunn diode mounted in a resonant cavity. So here we can see the different graph showing the threshold voltage. So the materials which have the Gunn effect are gallium arsenide, indium phosphide and gallium nitride. These are direct band gap materials. That is, they have more than one valley in the conduction band, and the effective mass and the density of the upper valley must be higher than the main valley. So this is the reason we are getting the negative differential resistance. So it is biased in this negative resistance region to produce the Gunn domain. So once the domain is formed, the electric field in the sample falls below the negative resistance region, and there inhibit a formation of the second Gunn domain. So as soon as the domain is absorbed by the anode contact region, the electric field in the sample rises, and then the domain formation can again take place. So this is the region current AC current oscillations are produced. So here to make Gunn oscillators, we need a Gunn diode to be placed inside a resonant cavity. So there are two major components. One is DC bias circuit and tuning circuit. So this is necessary for maintaining the sustained oscillations. So here we can see the Gunn diode placed inside a coaxial cavity. So here the tuning circuit, the oscillation frequency depends on the active layer of the Gunn diode. It can also be externally tuned by mechanical or electrical. So in case of electronic tuned circuit, the control can be brought by using the waveguide or microwave cavity or varactor diode. So this is used to produce the AC current oscillations at a particular frequency. And then some applications are, it can be used as a low power oscillator at micro frequencies and radar transmitters, pulsed Gunn diode oscillators and transponders for air traffic control, low and medium power oscillator micro receivers, and they can be built using semiconductor with high electron mobility and frequency response. So terahertz oscillators can be used. Gallium arsenide and gallium nitride semiconductors are used to make Gunn diodes in the gigahertz and terahertz applications. And they can produce extremely high energy levels, so they can commonly used at microwave, millimeter wave and terahertz systems. So we can have a small assessment. So gallium arsenide is used in the fabrication of Gunn diodes because gallium arsenide is cost effective and it is less temperature sensitive. It has low conduction band electrons and less forbidden energy gap. So the answer is less forbidden energy gap. So these are direct band gap materials, so it can produce oscillations. Next question is, when the electric field applied to a gallium arsenide specimen is less than the threshold electric field, the current in the material increases linearly or decreases linearly, increases exponentially or decreases exponentially. So the answer is current in the material increases linearly. Okay, thank you for listening this video.